Purdue.
Thank you, Mr. McNaught.
Purdue?
Purdue data science.
Congratulations.
Thanks so much.
That's awesome. Excellent.
Today, sir. Today.
Awesome.
Yeah. New spring starts that.
I wish I was a senior.
Me too. Oh, wait. Okay. All right, everyone's here. Congratulations. That's awesome. All right. Have you been to campus? See, it's shocking to me how many people like they're going to these schools. Like, yeah, I've never been there, but
Have you been to Indiana before?
No.
Have you been to Rice? No.
yeah.
Texas.
All right. What are we doing here? We are going to. All right, so we're going to talk through a little bit more. I'm recording, so just remind me I'm recording. We are going to talk through. Am I recording? Yeah. Okay. A little bit more on our disjoint sets. Okay. And I'm going to try and build some disjoint sets. Okay, some disjoint sets implementations. So what do we have so far? We have a couple of different ways that we've built this. Like they're all disjoint sets, and we could actually write. Let's go ahead and do this. Everyone, go ahead and open up IntelliJ, and let's go ahead and write our interface.
New project.
Yep, new project. We're going to call it disjoint sets. And that's going to be actually the name of our interface as well. Public interface. And then we got to figure out what's going to go in here. So if we look at our quick find, we sort of remind ourselves what this looked like. What are the two things that we're checking with disjoint sets? We have two methods that we have been talking about with disjoint sets. And if we come back, I can come back over here. Yeah, so with our two things is connect. That would work. Okay. So we have connect, and what's the return type on connect? Okay. And what do we pass in for parameters? Yeah, we're gonna just use ints for this thing. Okay, could we theoretically make it such that we could connect countries and people and dogs and everything else? How would we do that? T. We'd have to use a generic type, right? Type T. But right now we're just gonna use ints. So we got void connect, and then is connected. I don't know why I'm writing it up here because we're gonna have to put it into our interface. So let's put it into our interface, right? But these are our two methods. So we've got void connect int A, int P. Oops, that's a Q. Whatever. In Q, int P. There we go. P's and Q's. P. What type of thing is this connected? What do you think? Yes? No? Boolean. Y'all are looking up here. You guys write the methods. Boolean is connected.
Can we set it to true?
You tell me.
I know. False.
Okay. What is false?
Is connected.
Where? Where are you setting it to equal to false or true?
Is connected
Where?
in the method.
So theoretically, is this a method? Not really. What is it? Huh? It's an interface. So it tells us what methods need to be implemented, but we're not implementing them. So we don't give it any value, right? So we're gonna have is connected. And again, what are our parameters? Yeah, in Q, in P, whatever, in A and B. Right now, do we need anything else? No, that's all we have for right now. So we should, and I won't make you go through this, right? But we went through what are our different variations of this thing so far?
So find good stuff, like quick find.
Quick find, right? So I can find things quickly. We did actually start with our list of what? List of sets. You got it. We sort of had this list of sets implementation. Then we had quick find, and then we had what? Quick union. Yep. So we can optimize sort of one thing or the other. Quick find was, which one did it optimize?
It's connected.
Is connected, and it got is connected to runtime of what?
One.
Oh,
one. Oh, one.
oh, man. No, oh.
It was O of one.
Yeah.
Yep. Also theta of one, right? Because
Yeah.
can they be different? Not, I mean, not realistically. You can't get faster than one, right? So if it's O of one and it's theta of one.
The ins or the O of one is theta.
Say again?
What's different? The ins or like?
Oh, no, sorry. So yeah, the ins have to be, right? The theta of one versus O of one. Yeah. Okay. So that optimizes is connected, quick, and then at O of theta of one. And then the quick union gave us what?
Like a shorter.
A shorter connect.
Yeah.
Yes, a faster connect. What's our problem with our connect? Come on. Do we have any problems with our connect so far? Yeah.
Well, for quick union, is connected, it's gonna be slower.
It's going to be, it will be slower. It won't be O of one. But what's the problem with our?
It doesn't care about the length of the tree, the height of the tree.
Yeah, so we have to be careful with the height of our tree. So is everyone comfortable? How would we actually let's talk about this. I'll give you the implementation. I can't go backwards because that side's missing. This implementation is pretty straightforward. The quick find implementation. And if I come over here, I can say quick find, and I can implement disjoint sets. And if I do that, I shouldn't have any issues. Okay. I'm just going to talk you through this one. If you want to code it all up, you can. Underlying this thing, what's the underlying structure of all of these after our list of sets? An array, right? It's an int array. Quick find is going to populate those all with what? For quick find, what am I populating the array with? For quick find.
Well, they're themselves.
Themselves. I'm going to iterate through this thing and populate each box with its own index. Okay, right? So if I have these, my indexes, right? So I populate each one of these with itself, because what is each one of those things? We think about this. This is not a good example. It's its own parent. It's its own root, right? We want to use the word root here because it's going to help us. Okay, it's its own root when we do this. So then when we start connecting them up, right? 0 is its own root. So when I connect 1, 0 becomes 1's root, 2 becomes 1's root, or 0 becomes 2's root. 3 is connected to 5, so 3 is its own root. When I connect 5 get 3 as its root, 6 is its own root, right? And then so when I connect, what was I connecting here? I don't know, for 2 and 3 or something like that. When I connect 2 and 3, I'm going through and I'm saying, oh, connect 2, 3, and then I go see what 3's root is, and I just change these all to 3, right? And we can see the time complexity of that is I have to go through potentially n things or n minus 1 thing, so it's n. Okay, all right. And then, oh no, don't mess around with that. I'm in the middle of my homework assignment. Right there. That's my homework right there. Okay.
You still taking that class?
Different class. Okay, so this is our constructor. We're just creating this new, we're filling in the length of the array with n, and then we populate themselves. Connect is a little bit more complicated, but is connected just does what? For quick find, remember, what do we optimize here?
Like if they're equal.
If they're equal, we just say, hey, is connected is the thing in that space, right? At index P is the same at the thing at index Q. In other words, if I start here, right, and I look, these are my buckets, these are my indices, and let's say I connect 4 and 0, right? The thing in the bucket, oh, I'm gonna erase these, that's the problem. Becomes 0. And then I simply say, okay, is the thing at index 0 the same as the index 4? Yes. Well, they're connected. And it's one step because these are each, I don't have to iterate through anything. I'm going directly to those indices. That's what an array allows me to do, right? That's why the array is the powerful backing force here. Okay, and then connect isn't that much harder. I'm simply going to, and I don't really have to do these first two steps, but it just makes life easier. I iterate through this thing and I simply go look if the ID at I is equal to the ID at P. And then if it is, I set the ID at I equal to the Q. In other words, what that step right there is doing is it's the piece that's going through and it's saying, hey, when I make this connection, when I connect 2 and 3, right, I'm saying here's 3 is what I'm looking for in here. Okay, and I go grab everything that has 2's, what's in 2's box, which is 0, and I go through everything that has 2 in it, or the 0 that's in the 2 box, everything that's a 0, I'm going to grab this and I'm going to put a 3 in there. Does that conceptually make sense? Okay, and that's what this code here is doing. It's assigning the PID and the QID. It iterates through if the QID equals the PID, like, okay, remember this is the 3, right? Or excuse me, this is the 0. If it's got a 0 in there, I'm going to change it to a 3. And I'm done. And it's a void method. Yep. And we're done. And if you go step through this, I think we looked at it last class. Quick find is going to be a little bit different. So what are we doing with quick find now? What do we change for quick find? Quick union. Sorry, that was quick find. Quick union. Thank you. What do we change for quick union?
All of it.
What?
Like you have to change all of them.
You don't have to change all of them.
We attach like there, we attach the 3 to the 0 instead of the end of the, instead of.
Okay, so we did a couple of things here, right? So the first thing we did is what Tony mentioned a second ago, which is that I didn't populate. You know what? I'm going to stop using those because they're a little bit confusing this way. Okay. 0, 1, 2, 3, 4, 5. Okay. So this is my array. These are my array boxes. What am I putting in the array boxes now?
-1.
Now I am doing -1. And we'll see why this can be helpful. Okay. But I'm going to put -1 in here. And then when I connect things, I'm going to just connect up to one number. So we get this tree structure that gives me a root. So I can think of this visually in 2 ways. One is just the array, excuse me. And 2 is as a tree. Okay, so if I connect 1 to 0, let's think about this. I connect 1, index 1, I connect 1 to 0. What do I do?
Change 0 and -1 under 1 is 0.
Yep. So I say, hey, 1 is connected to 0 and 0 is its own root. Should I put the indices underneath? Will that make actually, is that, why do I feel like I always visualize indices underneath?
I think that's also, it shows it in the visualizer.
Yeah, it does. Is that better? That's better. Okay. Now I connect 2 to 1. Well, all I have to do, right? How many things do I have to change here? 1. What thing do I have to change? Yeah, and I said, hey, 2 is connected to 1, now I can go to 1, 1's connected to 0, and 0 is its own root. So now I'm starting to build a tree structure in here. I say, okay, let's connect 4 to 0. Well, that's easy, I just change this to 0, 0 is -1, 5 is still its own root, 3 is still its own root. And I can connect 3 to 5, I just have to change the one number. Right, so now is connected becomes, what does it seem like it is right now, at least? What steps I just went through? How quick was that?
Theta then?
Did I go through n numbers when I changed one? Think about it. What did I do? I just changed
Oh, no.
Oh, one.
O of 1.
Yeah.
Yeah. Okay.
Because all I'm doing is changing one number. I connect 5 to 3, I change one number. 3, I'm done. O of 1. Is it O of 1?
No,
Why not?
but it's like, how we talked about it, you like connect everything to the previous one, like open.
Why? What do you mean?
Oh, wait,
But that's not the reason why it's not O of 1. The connected would still be O of 1, theoretically-ish.
Is
Yeah.
it because you have to go back to the original connection, like to get the 3, you have to go to 1, then back to 0?
Well, that will be an issue with is connected.
Yeah.
Because how do I check if two things are connected now?
If they share the same root.
Yeah. And so what do I have to do if I say, hey,
For loop. Or,
is it a for loop?
you have to like go back to its like root. So sometimes.
Yeah, so now you were talking about recursion, right? Now here's where recursion might come into play, because if I go say, hey, so give me 2 numbers. Anyone give me 2 numbers, quick.
6.
6 and what? There's no 6, get out of here.
1, 5.
1 and 5. Are 1 and 5 connected?
No.
Well, I don't know if 1 and 5 are connected right away. What I have to do is climb the tree. I say 1 is connected to 0, 0's, then this is, right? 0, that 0 is the top of this tree. And then 5 goes to 3, up 3 is its own root. They are not connected. I can climb the tree in each case.
Yes.
Was that O of 1?
No.
No, it wasn't O of 1. Okay, and what Tony's talking about is that if we get this messy tree here, we've already looked at most of that. If we get this messy tree here where I connect 0 to 1, 2 to 1, 3 to 2, 4 to 3, then I get this tree. And if I try to see if something's connected to 4, what do I have to do?
Go all the way
Go through all of them.
All the way up, which gives me now O of n. So this is sort of our worst case scenario, and that's why it's O of n, because it could be much faster. It could be O of 1, or O of more or less 1. And it does come down to something essentially that Gordon said last class, okay? Which has to do with how we connect the different structures, okay? I just lost out where I was. Okay, how should we change the parent? Hang on. Okay, let's go through this. All right. So how should we change the parent list to handle this connect operation? 5 and 2. What are our choices here? Connect 5 and 2. What do I have to do here?
You could connect 3 to 2 or 3 to 0.
Well, how do you immediately jump to having to connect 3 to something?
This 5 is connected to 2.
Yeah, I can't connect 5 to anything. Is everyone clear on that?
Yeah.
Because what would happen if I connected 5 to 2?
Lose 3.
I would lose 3. Yeah, exactly. 3 would not, 3, I want 3 because 3 is connected to 5. And I want, if I connect 5 to something, I want 3 to go along for the ride, right? Because they're connected too. But if I just connect 5, I lose 3 and 3 seems to just be its own root still. And I just screwed that up. So I do have to climb the tree. I get to 3. And then I could connect 3 to 2, which I think, Tony, that what you just recommended.
Yeah.
Or I could connect 3 to what?
0.
0. Which one's better?
0.
0.
Why?
Oh, because you have to go through the
Mine's
rest.
3 is shorter.
3 shorter.
Yeah.
Okay, so I ultimately want to connect 3 to 0 to keep my tree height small. Okay, so there we go. We just sort of talked through all that, right? And then what changes in our array when I do that? If I connect 3 to 2, 3 to 0?
And
-1 becomes 0.
Yeah, the only thing that changes in the array is the one number. Okay, I say 3 is no longer its own root, it's connected to 0. So then I could figure out what else it's connected to. Cool, okay. This is our performance issue. This is what quick find looks like. I'm going to give away this one too. Am I going to give this away entirely? Okay, so quick find, and I'll go through the same steps here in that I should implement disjoint sets, which shouldn't give me any trouble because I've already got all the things in here. My parent array is the same. When I go through my constructor, what's the only difference with my constructor? Populate it with -1s. Let's go ahead and do this one because our quick find is going to be the basis of the rest of the stuff that we do. Code this thing out. So figure out what you want for a constructor, figure out what you want for your connect method, figure out what you want for your isConnected method.
should we have our completed quick find final, or?
We're just going to skip over quick find. If you want to go back and code quick find, we can. But we're going to not do that right now. You'll notice that what have I done here? What's the one? No, start coding and then we'll talk about it. And you guys can communicate around this. You may collaborate. Yep.
Have we done something called arrays.build?
We have not, no.
Saying
You could use it, but don't.
maybe like the yellow line thing replaced by.
Yeah, you can replace this with better code that says arrays.fill.
Yeah, method called, but I don't even know what it is. Yeah, don't worry about it. Just do what you do.
Actually, go ahead and just click on the Go ahead and click on. Good.
Oh. Oh, I just like a shortcut.
Yep.
Okay.
You can leave it there if you want to.
Alright.
Super fun.
Yep.
I actually something with the house and we're just gonna pop drop.
Wait, this.
So you should have a constructor. You should have a connect and an isConnected. I put my isConnected out of view because
Is
it's not a, I can't hide it.
is your find is connected? That's,
No. So good question. Look at the signature on find.
oh, it has one instance.
And it's private.
So we need a find.
Well, there's other ways of doing this, but I'm going to recommend that you use a private helper method called find. You could also call this, you could call it a whole bunch of different things. You could call it find root. Does that help explain it more?
Oh, yeah,
Okay. In other words, this is the method that's going to do what?
find the root.
Climb the tree and find the root.
So
Okay.
do we need a is connected?
Uh-huh. Absolutely.
Okay.
You have to for a whole bunch of different reasons, but you're also primarily, why do we have to have it?
Oh, so then we don't when we connect someone, we don't append it to the end, we can put it to the root.
No, you're asking, we're talking about why do we need the isConnected method?
To see if it'll connect it, right?
Yes, and someone help them out. Why do we have to have isConnected?
So you can call the find.
Yeah, find method just helps me inside of connect and isConnected.
Isn't that the whole point of like disjoint set? Like.
And how do we know that, Tony?
Just.
Oh, it's in the interface.
It's in the interface.
Yeah.
I'm implementing disjoint sets. If I don't implement it, it ain't gonna work because I've implemented disjoint sets and I've said I have to have disconnected.
That's what I
It's
was
part of the point of disjoint sets.
That's why I was confused, because you don't have it.
I do. That's what I said. I'm hiding it because the
Oh.
answer is like the code is there. Here, I'll do this.
I just thought.
No, it's all good. I'll just I was trying to like, sort of disappear all the codes. So I'm not giving away all the answers. Here you go. Ready? There you go. There's your is connected. Find is just a helper method that climbs the tree.
Oh, so it's not just like return. everything.
Well. So which one of these is easiest? Everyone, so constructor should be pretty easy. Yes? Has everyone got the constructor written?
Yeah.
Everyone?
Sorry.
Okay. And I'll just show you, this is just kind of fun. We can replace this line. Daniel, what can I replace that with? It's funny that's not giving me the hint.
I don't know. Alright.
Oh, no, I'm frozen. All right, so I can say parent equals new, and I have to finish parent. I go up to num.
Instead of a for loop, you can do capital A arrays dot fill.
And this is handy for certain things.
There's the array we're filling. So parent
Takes the parent,
and the value we want to populate it with, so negative one.
and if I'm filling an entire array with just things, this is just iterates through it and does that. Now the reason, what's my problem? I don't have you also have to import the arrays. Right, java.util.arrays, which is fine, but you can do this. It's handy for certain things. There's certain algorithms. We do the sieve of Aristophanes. You can do this with a Boolean array. And the sieve of Aristophanes. Anyone know what the sieve of Aristophanes is? It's actually pretty cool. It goes along with like the greatest common denominator Euclidean algorithm.
Yeah.
The sieve of Aristophanes, nobody? Gives us prime numbers. It's a prime number. We'll call it a generator, but it's pretty cool. Little hard to code up, but not too bad. So which of these methods is going to be the easiest to figure out first?
Yeah.
Okay. Connect should be really quite straightforward. Am I? I'm going to say is connected is even easier. I will say that you want to probably use your well, when we did this. Wait, I gotta hide that again. Gotta be tactful here. Okay, when we did this connection, what did I decide I wanted to connect 3 to? 0,
Which is the root.
which is the root. So what method might I want to use when I say connect? Find. I want to use find.
So we need to code find first.
No, honestly, I would code find last. I would say, I'm gonna have this method that finds the root. Okay, I would code up everything else first and then figure out find. Because do we think the find's gonna be the hardest piece of this thing? Probably. Because think about what is connected. What am I checking for is connected?
If they have the same root,
So what do I say?
return. Find root.
Find equals find.
Find equals find, and I'm done. Right, so literally that's all my is connected is. Whoops. I put a whole bunch of spaces in there, now I'll get rid of them. So this is just find P equals find Q. And we're done. Is connect, or connect is maybe 3 more lines than that. Something like that, yep. Looks right to me. Now try and figure out your root find method.
Oh, I have.
You got it right? Your connect looks a little off. Check with Tony what he's got there. You guys can communicate. You guys can communicate, even if I can't.
We gotta do
Uh,
That doesn't look rough.
And do this.
What is connect
Yeah, you do this.
what do we
You do that,
have to do
you do that.
with connect? Remember what we're trying to connect?
And
What
then
did we say we want to use in connect?
But isn't P and Q like the actual, it's not like the index, right?
Wait, so we need to connect like
well,
the.
it's the index.
I'm trying to connect 2 and 3. It's the index.
Oh, it's the index.
Right, because remember, for this structure, our index is our identifier. And what's in the array, it's a little bit weird because this is our identifier. What's in the array is our parent. And it's a little bit of it's flipping an array on its head essentially, right? Because we're not used to using the index as the identifier. Usually what's in the array is our identifier. Here, that's not the case. So you got to be a little bit, think about it a little bit differently. If I think about the is connected, right? Everyone's eyes up here for 1 second, so we just make sure we're on the same page. If I think about is connected, I'm passing in, I don't know, is connected, what did we say last time? Down to 1 and 5. So is connected 1, 5, right? So what I do is I go to 1 and I say, okay, find the root of 1. 0 and 0 is its own root, so 0 is the root. So that also gives us a little bit of hint about where I need to go with find. Do I go to -1?
Yeah.
No, I don't, because every root is going to be -1. I want to return 0. I want to return the thing before I hit -1. That's just a sort of forward thinking on find. Because if I return -1, every root's going to get there. Doesn't give me an answer. They're all going to be connected if I do it that way. Okay. So if I connect 1 and 5, I climb 1 to 0. Well, 0, this gives me a find, gives me the number 0. Equals, okay? And when I go to 5, I climb to 3. 3 is its own root. This gives me find equals 3. So I say, hey, find P equals find Q. Well, 0 does not equal 3. And I get my Boolean response. No. 1 and 5 are not connected. Okay, so hopefully that can help you think through your connect. So Tony, if you've got that in there, build one and run it and see if it was working. So we'll just use, for today, we'll just use a main method. When we build one of these things, we just say, hey, quick union equals new quick union, put in a set of numbers. For right now, just keep it 9 or 10. Don't make it bigger than that. Start connecting things, see if that works. And then you can call something like, QU dot is connected, 1, 6. Okay, this one's a little bit bigger. Then you can go in and debug it, run the visualizer. Tony, you have the visualizer in there now, right? Okay. I'm not even going to ask why, but you should. Everyone should have the visualizer in their IntelliJ.
How do I get?
Someone tell them how to get it. Okay, so I stepped through this thing, right? I've got an array of -1s. I connect 1 and 9. What's going to happen?
9 becomes 1.
Yeah, what's in the box of 9? This should become 1. Oh, it went the other direction. That's fine. Does it matter?
That 1 became 9.
1 became 9.
That's just reversing.
Yeah, it should be the same thing. Let's find out. I connect 9 and 2. Well, 9 connects to 2. 2 and 3. 2 became 3. 3 and 6. What's going to happen now if we think about it? The numbers are a little confusing, right? The identifying by the indexes versus the numbers that are in here.
3 becomes 6.
3 becomes 6, and then 1 and 6. I'm checking is connected 1 and 6. So what do I have to do now? Is connected. What's in 1 is 9. 9's to 2, 2's to 3, 3's to 6. 6 is its own. So the root of this tree is 6. I did go backwards here, didn't I?
Right.
Okay, so the root of 6 is -1. But now obviously, when I checked against 6, do I already know the answer? Yeah, this was not a good choice. I wasn't really paying attention because what's the root of 6? What's the root of 6? What does -1 indicate?
It's
Oh,
not-
not-
That its own root.
So that's never gonna be true.
So it's not connected.
-1.
Mike? Why not?
If it's its own root, it's never gonna be the same as.
But think about 6. Right? Think about the way I climbed that. I said 1. 1's root is 9. 9's root is 2. 2's root is 3. 3's root is 6. Molly, get off here.
Molly, where are you?
So the answer is true. Think about it. If I said, if I said, what's the root, are 5 and 3 connected? Do I know immediately by looking here if 5 and 3 are connected? I kind of do right here, right?
Yes.
So I climb the tree, I say 5's root is 3 and 3 is its own root.
It is, oh.
3 is its own root, they are connected. It's just, this is just the head of the tree, it's the root of the tree.
Oh.
Okay.
Right? You'd think that whoever this is would figure out that they're trying to connect to my board.
There's no way to override it.
Yeah, I can turn it off for a minute. There we go, figured it out. Okay. So when I go over here to is connected, did I step through it already? I don't think so. I go to console. Oh, what did I not do? Got to do that piece. Oops, button. So when I do that, I'll just run it this time as opposed to doing all the rest of the steps. And it should tell me true once it runs. Right, because 3, 1, and 6 are in fact connected. Okay. I'm not keen on the way I did that connection though. So I'm going to connect back the other direction. So I'm going to freeze my screen so you can't see what I'm doing. See if that does things the way I want it to.
They have the same root that. Oh, you. Well, whatever you're wearing. They have the same root, right, and they're connected.
All right, let's see if I did this properly and reconstructed it. Okay, so when I connect 1 and 9, what I really want to have happen is what? I want 9 to become 1. There we go. Okay. 9 and 2, right? I connect 9. Yep. Right, they're both at 1, 2, and 3. I should get this to become. Now, see, why is it going to 1?
Because. Connected to 1?
Well, does this sort of make sense? Yeah, 2 is connected to 1.
Yeah.
2's root is 1.
Next to its root.
I'm connected to the root each time. Right, so I want to connect to the root each time. So this is right. It's a little bit different than maybe we thought about 3 and 6. Well, now I've got 3 and 6. So what should 6 become? It should become 1. And now I've got a totally flat structure. If I think about this visually, every single one of those, why is that good? How many steps do I have to take to get to a root in this structure right now? It's one, I look and I say, okay, what's its root? 1, it's its own root, and I'm done. It's O of 2, which is O of 1, but it's O of 2, right? So I'm not creating this depth tree. I'm connecting everything to the root each time. Now, if I connected some other things first, let's do that, and that will make maybe more sense. So instead, I did this very linearly. So let's not connect 2 and 3. Let's connect, let's say 3 and 4. Yeah, I'll make another tree here. I'll connect 3 and 4. I'll connect 4 and 6. And then I'll connect QU dot connect, let's say 6 and what? 9. Sure. Okay. So now this should look a little bit different. Whoops. No. Debug. Bum, bum, bum. I broke it. There we go. Okay. So now let's try this again. Create this thing, all negative ones. 1 and 9. What happens to 9? Becomes 1. I'm saying, hey, 9 is connected to 1. That becomes 1. 9 and 2.
Becomes 1.
2 becomes 1. Now 3 and 4.
4 becomes 3.
4 becomes 3. Yep. 4 and 6.
6 becomes 3.
No, 6 becomes 4. Yeah, 6 becomes 3.
6 becomes 4 or 6 becomes 3? It becomes 3 because I'm going to the root, right? I'm connecting to the root. It just saves me trouble. And then 6 and 9.
9 becomes.
Yeah, and
Yeah,
that
3.
rate is 3.
What happened?
Like, it didn't change.
Yeah, it did. What changed? I can't go back. I wish I could go back a step. That's the only thing. If someone can figure that piece out,
They don't have a function.
I don't think so.
Tony built that.
What happened? I connected 6 and 3. Well, what was 6's root?
Next 6 and 3.
I connected 6 and 3 in my last one.
Wait,
Oh.
9, right?
1 became 3
The root of 6 is 3.
because the root of 6, right? So if I could, now let's pick let's do it is connected now. Is connected 1 and 6. 1, I go to 3. 3 is its own root. So the root of 3 is the root of
1 is 3.
1 is 3. Right? And then I go to 6. Well, I already know the answer, right?
But it's 3.
Because it is 3. But theoretically, I should go to 3. 3 is its own root. All good. If I tried to connect, let's say, the root of 9, if I think about it, because we expected 9 to change there. Well, I go to 9, right? 9 gives me 1. 1 gives me 3, and 3 is its own root. So this one that last connection was a little bit weird. But it works.
That's it?
I'd have to think about why that happened the way it happened, but it works. All right, so how are we doing with do we have our connect now? So is connected is very straightforward. How many calls to find should we be using in connect? How many calls to find
Oh, 1.
Just, in connect.
in connect?
2.
Why?
Trying to find the root of P and Q.
Yeah, you have to find the root of both.
Oh, because you also have to connect B back to Q.
Well, we could, I mean, so if we come back to our picture, could we just connect, whoops, freeze. Could we just connect, right? Do I have to find the root of one of the two? If I connect 2 and 3,
Yeah.
Just
I could connect 2 to 3, but what do I want to connect 3 to?
It's a 0.
0, which is the root. So I have to find the root here and find the root here and connect them.
oh.
So I should call find on P and Q. And then I'm simply going to set Q. What am I gonna do then? What happens here? If I do this correctly, what happens in the array?
Q becomes the root of P.
So Q was 5. When I find 5, I go to 3 and I get 3. Okay? Now this is one step too far, isn't it?
Oh,
Wait, if you're connecting 2 and 3, why do you need to find the root of 3?
Well,
Just set
'cause-
3 to like the root of 3.
I'm connecting 2, sorry, connecting 2 and 5.
Oh, yeah, like, oh,
you can't connect 5 to 0.
I can't connect 5 to anything, and I could connect 3 to 2, but I'm gonna end up with an ugly tree. It's gonna be less than optimal.
Isn't that like horrible memory then?
It's not so much horrible memory, but what it's gonna do is create that long tree. That when I call is connected, I have to walk up that tree for the find method, right? So if I did that, let's think about it. If I said, I did that, and I connected down here and I got 3 and then 5, and I said, is connected 5 and 4.
If
Well, now I have to walk all the way up the tree of 5.
So full of N instead of full.
Yeah. So isn't it just parent at find P equals parent at find Q?
That's is connected.
Yeah, that's connect, right? Like, parent at index
parent?
find P equals parent at index find Q, that connects the 2 roots.
Not quite.
Just do it one time. Like,
You want it, you're setting, because think about what you're changing. I find 5.
Yeah.
I get 3. Right? And 3 is the root, right? So I come over, I go 5, 3, 3, 3 is negative, so I'm going to 3. Okay,
mm,
now when I climb here, I get 2, 0, 1, or sorry, 2, 2, 1, 0. So the root here is 0.
so parent root 2.
Do I want to change anything here?
Yeah, no, wait. No, you only want to change the root of
Just
3.
want to change the root of 3.
Yeah,
So I want to set this in here.
root 2.
This, remember, the only thing I'm changing in the array. So parent, that's our name of our array, right?
Yeah,
Parent at what?
root P,
Find P
oh yeah, find P,
equals, how did I get to 0?
parent at find Q.
Not parent. Because I don't want to get, that's
Oh,
parent
Oh, find Q,
at find Q.
it's just find. Q.
It's just find Q.
Oh,
Yeah.
Does that jive? Does everyone understand what we just did there?
Can you swap find Q with find P?
Yeah,
Okay,
no.
What?
You can't,
Why?
because find Q. Wait, hang on, let's think this through for a second.
Yeah, it's kind of messy, like the
No, you
order.
can, but there will be no order to do that, right?
Well, that happened to me earlier.
You can, but it affects the height of the tree.
That happened to me like last weekend, like 2 minutes went away and I just like.
Parent at, no, I did flip those two. So you could, so if we go back here. Let's think about, let's go through this one more time. So P and Q, we'll assume that we want to go the smaller is P. So if we say P to Q 5, we want to, parent at find Q. Because we want to change, in the array, we want to change 3's root,
Oh, right.
Q's root, right? So 3, we find Q gives us 3, right?
Yeah.
And I want to set that in the array, parent at that thing, equal to find the root of P.
But you could change 0 to,
And we're gonna see why and when we're gonna wanna do this.
Like, that's
So
the
actually, I'm being a little bit tricky here because we're gonna change this in a minute. And then we'll see why we're gonna change it in a minute.
But in your interface, which variable you have first P or Q? Because I don't know if I'm doing this backwards.
I got P. But again, it doesn't really, whoops.
Just for saying P and Q so much, I don't want to.
Totally cool, but I just did A and B and Q and P. It doesn't matter what I have in the interface, right? How you put it into your quick union. I like to have the P be the lower number, but it doesn't matter.
It doesn't really matter, because.
It doesn't matter.
If you use like find, they're all gonna give you the root, and so it
Yeah.
doesn't matter which one.
Right, so this, I could just simply do find Q here, right? And this equals find P,
Yeah,
right?
you actually like
I get rid of that.
test we find the size of each like set before we like connect them to see which is faster.
You're totally ahead of the game.
Because there's no point of like going one direction.
Totally right. So if we have, like, if I think about it, which one of these do I want to connect to the other one?
Shorter.
To the taller one, yes. Right, so if I said for whatever reason, if I passed in connect 5, 2, I wouldn't want to connect 0 to 3. I want to see which one of these things is smaller.
So size.
You're totally right. And then connect the smaller one to the bigger one. That's the next optimization. So we're actually gonna you just totally open that up perfectly for me. I'll pay you later. Okay, so this is our quick union, and we'll come back to find in a second because we haven't figured that out yet. I'm going to show you sort of the optimization here, and then we'll come back to find. So we have our runtimes. I think it's here. I hate right on this board, and I don't usually do it. List of sets, theta of n, O of n for connect, O of n for is connected. Quick find, theta of n, theta of 1. Quick union gave us theta of n, O of n for connect, and O of n for is connected. Doesn't that seem like it's worse? Why do I have O of n for connect?
that's the
Next
worst case.
O of n means worst case. Worst case, and what's the worst case with connect?
Well, then,
Check the root of the.
I've got that long hanging tree when they're all connected in a line. That's worst case. That's O of n. Okay. We're not going to usually run into that though. Okay. So we can get tall trees. That's one thing that's going to be bad. So what do? We do weighted quick union. So this is exactly what Gordon is essentially saying. Weighted quick union says, hey, okay, if we have two trees, we're trying to connect 2 and 5. We have two choices. We can make 5's root into the child of 2's root. We can make 2's root into the child of 5 root. In other words, we can go, we're trying to connect these two things. I could connect 3 to 0, or I could connect 0 to 3. Literally the problem we just looked at. Which tree is better?
3 to 0.
Yeah, this is better because it's not as tall. Okay? And the height of the tree matters. And we'll get into more sort of formal analysis of why the height of the tree matters. Okay? So we're going to do that. So one possible approach to this is keeping track of the height of every tree. Okay?
Instance variable.
An instance variable that kept track of the height. So I'd come here and say, well, this one's how tall? 3. This one's 2. Connect 2 to the 3. Okay. Does that sound good? It does sound good.
Wait, the previous one, the one, well, how is the one on the top a height of 2, not 3, on the right side?
Because you have to.
Well, no, it's a reasonable question. Typically, when you talk about height, it's how many connections below the root are there.
Oh.
So this is theoretically height of 2. This is height of 3. We're not counting the root.
Okay.
So this is height of 2 and height of 1, ostensibly. Okay. So tracking tree height is really hard. It's not a straightforward thing. Okay. What's probably easier? What do we keep track of all the time? Count size. Just how many things are in there. Is that going to tell us the height of the tree?
No.
That's gonna tell us.
Yes.
How?
How?
You're tracking it, just you add something.
Well, it's gonna tell
Well,
us.
no, we're not track. What did I just say, Tony? I have a fear that you're not listening to everything that I'm saying. What did I just say about height? Yep.
It's really hard to track.
It's really hard to keep track of the height. It's pretty easy. It's really easy to keep track of the size. But the question is, do I know the height given the size? If I start from scratch. I do. If I start from scratch, okay, it is, you will always know, and we'll see why in a second, okay? So if we've got this thing right here, with our new rule, okay, we're always going to link the root of the smaller tree to the larger tree. What happens here? We're connect 3, 8. We only have 2 choices. Which entry changes? The parent at 3, parent at 0, the parent at 8, the parent at 6. Connecting 3 and 8, we've got a rule that says the smaller tree is always going to connect to the larger tree.
The -1 above 0 becomes 6.
So this is going to become 6. So parent at 0 is what changes. We're going with B.
Yep.
Other votes for B. B.
Yes.
B. B.
Wait, smaller connects to the larger.
Yep.
So 6 connects to 0.
So it's 8.
6 connects to 0.
Yeah, so 6 changes.
We all just said parent at 0.
Yeah. Well, it's just 6. Small connects to the larger one, right?
No, isn't the 0 shorter, like the,
Not, whoa.
it's.
We didn't, what did we say we're not going to track? Height, we're going to track size.
Oh, then
One
then
less
6.
Parent at
Oh, then
6. So we're going to connect this over here. Now, do we make a taller tree?
Yeah, like 1 slightly.
Yes, we do. We increase the height of the tree by 1 because if I connect 6 under there, right? So 6 would be in line with 5, 7, 8, 9 down here. If I connected the other way, how tall is my tree?
It's much taller.
2 more tall.
Well, it's shorter.
It's shorter because 0 would be connected to 6, right? So 0 would be in line with these 2 and all of these would be in line with this. This wouldn't get any taller at all.
But to get
But
to
the
0,
size
you have to
is
go
the same.
through time.
No, the height would still be 3.
Well, technically 2.
But if we did that, wouldn't we have to
Oh,
go
yeah.
through 9, through 8, through 7, through 6 to get to 0?
No.
Wait, how does the size doesn't change though, like either connection?
Size changes, sure. We just added 4 more things to the total size of the array.
Right, but
Of the-
if you connect like 6 to 0 or
Mhm.
0 to 6.
Size does not change. You're right.
but
You're
that
right.
doesn't- That's not, you can't use size, it's like.
You can. This is just an example, and I don't know why he does it quite this way. This is just an example. It's a little bit confusing. These are 2 already existing things that we're connecting. Okay, and that's the way we're going to do it. The reason is because if you, and we did in fact change, right? So here we changed 6 to 0. Okay. The reason we do this is, to do this, in fact, we don't do anything different with is connected. Connects just keeps track of sizes, okay? And there's a clever way to keep track of sizes, okay? Any thoughts on how you might keep track of sizes?
Connection, add count. Not plus 1.
Okay, and how would we keep track of that?
Connect.
We could have a separate instance variable, but what would we have to have for, if when we go back and think about these as 2 arrays, we'd have to have 2 instance variables.
As it's
You could have a separate array entirely separate array that said how big each one of these was. Totally, that's one way people do this. There's an even more sort of optimal, cool way of doing it. Well, is this -1 completely arbitrary?
Oh, if
Oh, just keep track of the size.
Keep track of the size right in here.
How?
How?
Like keep track of.
How big is this array now? Looks to me like everything's connected, right? So theoretically, is everything connected? Well, I know that I've got 7, 8, 9, 9's connected to 8, 8's connected to 6, 7's connected to 6, and 6 is 0. So they're all connected. How big is the total disjoint set?
Can we put it in a set?
10. Hang on.
oh, so like
Change that to 10.
Okay, well, go on, change it to 10. That's a little
Like,
confusing because that suggests that 0's root is 10.
Oh.
10 doesn't exist.
like
-10. I just increment this negatively to keep track of the size. I leave the negative sign in front of it.
So we know that it's its own.
So we know that it's its own root. If it's a negative, if it's less than 0, it's a root. And I just increment that number in the array to keep track of size. Isn't that really clever? Some really smart person said, hey, what if I just do that? So then, right, Mary's idea of keeping track of the array size with a separate array, totally common approach, okay? Create a separate size array, or just replace the -1 with negative weight for roots.
how do you increment that? Like,
-1 is.
I mean, like,
Whenever you add something to that tree, you're just going to take that size. Right, so if I have other sizes, I can do it a couple different ways, but you can have, so like, let's just take the second half of this thing, right? So -6, we know that these things were all connected. 9 was connected to 8, 8 was connected to 6, 7 was connected to 6, and 6 was -4 means that how many things are in that tree?
Oh, 4.
4 things. 1, 2, 3, 4.
So we just take the absolute value of the value of that index.
Is the size.
Oh. yes.
I think what I'm gonna do, what do I want to do? Let's talk through a little bit more on find because we got to finish our find method first. Okay. So let's come back over here. Whoops. Keep doing that.
It's connect, it's only 3 lines, right?
Connects one line now. Because well, the way I had it written on the board was right. We're gonna connect should be, yeah, what are we doing with connect? We got
First root.
2 finds, right? And we're gonna find, oh, I took away the pictures that I want. Here we go. I gotta get out of this for a second. Well, could I do this? Sure, we could do this picture. Okay. So if I think about this, let's say I'm gonna connect 5 and 9. Okay, connect 5, 9. Okay, so I'm gonna go, that's my P and my Q. I'm gonna say, hey, Q, find Q, that gives me 6. Right?
He was not.
And then I want to do what with this thing in the array at 6?
Change to 0.
I want to change that to find,
The root of 3.
right. So all I'm gonna do is I'm gonna say, and remember that I'm saying find Q gives me the 6. And in the 6th spot here, right? So I want to say parent
Find root Q.
at find Q equals
Find P.
find P. And I'm done. That's connect. Now we got to figure out connect or find. It's been a really long day. It's been a long week and I'm on duty tonight. It should, oh my gosh, I wish it was Friday.
David, 3 days.
Afternoon, I know, thank God. Okay. We do not have class on Monday. It is Martin Luther King Day. All right, so that's our connect. Cool? All right. Now we need to figure out our find method. So what needs to happen in our find method?
If we need a while loop.
You do need a while loop. So let's think about what that while loop would look like. If I'm going to use a while loop, almost do this. And if I say, we're going to use the same thing, find 9.
That's connected to 8, which is.
And I'm going to use my array here. So what's my while statement, Tony?
While I had like a temp variable, like current.
Okay.
If current is not negative, if current is not -1, then return.
Well, remember the change we just made with size, so maybe we adapt for that now too.
Or smaller than 0.
If it's smaller than 0, well, current is not smaller than 0. While the thing inside of the array at that number.
Wait, actually, you gotta do parent
There you
dot,
go.
parent current,
While I'm just going to say while
now look ahead.
parent at what?
Current,
Ah,
CUR.
Okay, so you're setting current equal to.
No, you can just say P.
Yeah, I would just say, well, we're using Q here. While parent or whatever, Q, whatever. While parent at Q is greater.
Or 0.
No, you need to update it,
Yeah, greater than or equal to 0.
so you need a temp variable for that.
Bless you. Holy cow.
That was, then you.
No, we don't. Do we need a temp variable?
Say Q equals parent Q.
Boom, right there. That's our next line and we're done. Well, parent at Q does not equal 0. One more time.
Q equals parent
Q equals parent
at Q,
at Q,
and then return Q.
return Q.
And you also have to do like a if statement at first.
Nope.
What if, yeah.
Wait.
For what?
If it is the first, if the root of that, of P is just -1, then it will give you like an index out of town.
No, it won't. It'll return P. It'll return itself, which is what you want.
It'll just
Okay.
hit the while loop and then return. Okay.
Well, parent at P, Q, whatever, is greater than or equal to 0. Parent equals parent at P, return P. It's just walks up the tree. Your job, okay, is to try to implement weighted quick union. Okay. Do we want to take 2 seconds and figure out what the step past weighted quick union is? What do we think?
One more after.
The last, yeah. Because weighted quick union, what are we going to have to do with weighted quick union? Or is that enough for homework, we think?
Wait, quick union, it
Well, remember, what are we going to do with weighted quick union?
have to change the negative to
Yeah, we're going to have to keep track of size. And then when we connect two things, what are we going to tell it?
decrement or increment size.
Well, I have to do that, but what else do I have to do?
You have to check if they have the same root.
I do have to do that, but we've already done that. We're done with that. We've checked that. You can add this to your existing code. What do I have to do?
You have to track the size.
Yes, and then what?
Then you have to increment it.
Compare the size.
root.
Compare the sizes. I compare the sizes and I do what?
Oh, that's that.
Connect the shorter one.
Connect the
Oh,
Smaller.
smaller to larger,
Oh,
not
smaller
shorter,
to larger.
not shorter to taller, the smaller to the larger. That's it. I'll let you guys work on that tonight.
I still don't understand why the size.
You'll see. Unless you really want me to take the next little bit to tell you. You know what? I think there's a little video clip that goes through it. Maybe I'll give you that for homework too. Yes.
In our connect, I mean, in the find root, it's all we have when we're, so like if we're finding 9,
Uh-huh.
the parent at index 9. If it's not negative, so it's not the root that we would track the size in. 9 equals the value of that index, which is like 8 in that other example.
Yep,
And then it just keeps going until.
until it gets to the -1. Remember, when it's a -1, it's not gonna give me -1.
So,
It's gonna return the number that has the -1 in the array.
okay.
And what Tony was saying was, hey, wait a minute, what if I have 9 and 9's its own root and has a -1? Well, it's gonna say, hey, is the thing in the array greater than 0? Nope, it's not. Well, I'm just gonna return 9.
Okay, that makes sense.
And I love the beautiful simplicity of this structure, right? We're doing all these different steps and cool things, and it's just an array.
It's like three lines, 1 line.
Yeah, and all the code is like super quote unquote simple, right? But it's this beautiful structure of, and this underlies like all the things that you do on the computer that are connected, social media and whatever else, right? This is it. All right, have an awesome rest of the day. And have a great weekend. I get to see you on Monday. No, Tuesday. Woohoo! Have a great